Hey everyone, so as promised, I was going to make videos for Objective 12, 13, and 14. We're just going to focus on Objective 12 right now in this video, and I'll have some other segment videos for Objective 12. This is just one of them. In this particular one, we're going to be talking about sections 7.3 and 7.4 from your textbook, this particular one. And we're going to talk about quantifying heat and work. Okay, so I'm going to start the video off with a little bit of a recap of what we talked about last time, which was basically how heat and work are involved in energy transfer. Okay, so last time we talked about how when a system exchanges energy with its surroundings, it exchanges it in the form of heat and work. Okay, so I'm just going to use my laser pointer here. Let's say the system starts with a certain amount of energy and it's transferring it to the surroundings. So as I said, it could transfer that energy from system to surroundings in the form of either heat or work. And we define heat in terms of Q and work as W. Okay, we've seen that last time. And according to the first law of thermo, we talked about how the change in internal energy of a system, also known as delta E, remember we described that internal energy of a system is E, but the change in internal energy of a system is delta E. We described this as the sum of the heat transferred and the work done. All right, so we looked at this equation last time. SYS over here stands for system, right? So again, the internal energy of a system is equal to the total amount of heat plus work done. Okay? And remember how I described that the delta E, the internal energy of a system, the change in internal energy, is a state function. All right? What does that mean? That means you start at a certain amount of energy and you end with a certain amount of energy. Okay? And the start point and the end point, you could just subtract them from each other, right? And you get the change in internal energy. Now, realize that we're not talking about the path of how we got from the initial energy to the final energy of a system, right? We're not talking about how we got from initial to final or final to initial. We just know we started it with a certain amount and ended with a certain amount, right? So that's what we call a state function, right? Just matters about the state, not the path to how it got to that particular state, okay? But if we want to describe the path of how we went from one energy to another, we can talk about the amount of heat and the amount of work done on the system or by the system, whatever you want to call it, depends on the situation. We can then figure out the path to how we got from a start point to an end point in terms of energy. And we talked about how we can then use this table to our advantage of figuring out, what the sign of delta E ends up coming about to be, right? So if you look at this table, Q for heat, it could be positive or negative. We talked about this before. We also have work. It could be positive and negative, right? When is Q positive and negative, and when is work positive and negative? So Q is positive if the system gains thermal energy. Now realize this table is describing what happens to the system, how the system changes. It's not describing the surroundings, okay? But remember last class we sort of added to this table. I'm going to go back to my pen here. So we can definitely add the surroundings portion of this in the table. We did it last time, but I'll do it again. So for Q, let's just focus on Q, heat. If a system gains thermal energy, what does that mean? It's gaining kinetic energy, which is associated, that's energy due to motion. And we talked about thermal energy being a component, basically a version of kinetic energy, right? So if a system gains thermal energy, where is it gaining it from? It's gaining it from the surroundings. Right? It had to get it from somewhere. And when Q is negative, the system loses thermal energy to the surroundings, right? So if the system's losing energy, the surroundings is going to come pick it up. So to the surroundings. Now, let's look at work. So work, when work is done on the system, it's positive. But if it's done on the system, where did the work come from? It was from the surroundings. So the work was done on the system by the surroundings. And work is going to be negative if work is done by the system, right? That makes sense. You can associate negative for work if the system is doing work on something. And what is it doing work on? Well, if work is being done by the system, it's doing work on the surroundings, right? So, or you could say work done to the surroundings. I think you're noticing a pattern here, right? It's either from the surroundings or to the surroundings, right? All right, and then delta E is basically the sum of Q and W, right? And if energy from either heat or work is flowing into the system, that has to be from the surroundings. Oops. And likewise, negative energy flows out of the system. If energy is flowing out of the system, it's going to the surroundings. Okay? Like I said, this table doesn't describe heat, work, or energy in terms of the surroundings. We just added that to the table to help you all make sense of what's going on here. Okay? And we did some practice problems related to this in last class. Hopefully you all remember that. If not, you could look at the problem set. I think that's problem set 23 to get a feel for how to apply these concepts to a problem. Okay, and speaking of heat and work, so last class I gave a great example of how you can visualize this concept of heat and work as far as energy. Okay, so we looked at billiard balls rolling down a table, pool table. Okay, and remember what I said, that the internal energy of a system, you can describe the system as this white ball right here. Okay, so that billiard ball, we can say that that's our system. And right now, the energy of the system, delta E, actually it's not even delta because we didn't change anything, it's just E. The internal energy of the system is 5 kilojoules. Sorry, joules, right over here. Remember that internal energy is the sum of potential and kinetic energy. But let's just say right now, the energy is all kinetic. It's not potential. It's all, we basically have 5 joules of kinetic energy for this ball. And we're describing that ball as the system. Okay? Now, let's see how the internal energy is going to change as the ball rolls down the table. So eventually it's rolling down, and on a smooth table, notice this is a smooth table. In a smooth table, there's some friction. And if there's some friction, that's preventing the white ball from hitting the purple ball with all the energy that it's got, which is 5 joules, right? And because of the friction of the table, some of that energy is lost as heat because of the friction from the table, okay? So half a joule of the 5 available, there was 5 total, half of that was lost to heat, Q, okay? But there's still 4.5 joules of energy left. And that 4.5 joules of energy is going to do work on the purple ball. And the purple ball you can describe as the surroundings. You can also describe the table itself as surroundings. So you have the table as the surroundings, and you also have the purple ball. So the white ball, which is the system, has lost half a joule of energy to the table, which is part of the surroundings, and it also lost the remaining 4.5 joules of energy to the purple ball, which is also part of the surroundings. Okay? Now what happened? You went from 5 joules to 0. Right? Now there's this white ball, the system has no energy. E equals 0 for the system, right? So what happened? If you ended up with 0 and you had 5 to begin with, let's calculate the delta E of the system. Delta E of the system is equal to the final energy minus the initial. Well, if we ended with 0 joules, but we started with initially 5. Oops. 5 joules. What's 0 minus 5? It's just going to be negative 5. Right? So that's the change in internal energy of the system. Well, check it out. That's what we got over here. Right now, all that kinetic energy is lost to the purple ball and the table. So notice that the change in internal energy of the system is negative 5 joules. Now, let's look at a situation where we have a rough table. For a rough table, we said, everything's going to be pretty much the same. There's nothing that's changing. The only thing that's changing is now we have a rough table, but the white ball is still the system, and it has 5 joules of energy. It's packed with 5 joules, right? That's your E initial. E initial is 5 joules. Okay? Now, it's rolling down a much more rough table than what we looked at before. And if that's the case, there's going to be more friction with this table. And the white ball, as it's rolling down the table with its 5 joules of energy, the friction from the table is going to have 3 of those 5 joules lost to the table as heat. And remember, the table is still the surroundings, okay? The purple ball is also the surroundings, right? If the white ball is the system, the table and the purple ball are the surroundings, because that's where the energy is getting transferred to, right? System to surroundings. So if 3 joules is lost as heat to the table, there's only 2 joules left that it can transfer to the purple ball as work, right? So the white ball is doing work on the purple ball, and it can only do 2 joules of it out of the 5, which is less than what we had before, right? But bottom line is that all of that 5 joules was transferred to the table and the purple ball, okay? And it's the same situation where delta E is also negative 5 joules, right? Because if you take 3 that's lost from heat, 2 that's lost from the work being done on the purple ball, you get negative 5. So the change in internal energy of the system is also negative 5. All this is telling you is that whatever the system had, delta E of the system, is equal to the negative of the surroundings. Right? That makes sense. If the system started with 5 joules and it lost all its energy to the surroundings, it's negative 5 joules. Okay, this is an example of that. Another thing we realize here is that no matter what path was taken, right? Smooth table, rough table, right? 2 joules of energy is work, 4.5 joules is work. The path doesn't matter, right? How the energy was lost or gained, it does not matter. Bottom line is we started with 5 and we ended with 0 in both cases. And the change in internal energy was negative 5. Right? So that's essentially what you have to take home here, is that the change in internal energy, it doesn't matter about the path taken, because it's the same for both situations, which is why it's a state function. Okay? State functions, like I said, the path does not matter, right? Only the state from initial to final matters. Now, if you want to talk about heat and work are not state functions because they're path dependent, right? We've noticed that there's a difference from the smooth table to the rough table as far as how much energy was transferred in the form of heat and work. It was different in each case. That is all path dependent information, but the change in internal energy for both situations was the same. And if the internal energy, the change of internal energy isn't path dependent, then it is a state function. Okay, so again, we're just recapping on what we talked about last time. Hopefully this makes sense. Another thing we talked about last time was heat being exchanged, between a system and surroundings, realizing that temperature and heat are not the same thing, right? We talked about this, how the temperature is just a measure of the average thermal energy within a sample of matter, okay? So you guys know that thermal energy is a form of kinetic energy, right? And remember what kinetic energy is. Kinetic energy is energy associated with motion, right? So if particles are moving really fast, really fast motion, what does that mean? That means the system that contains those particles that are moving really quickly are going to be higher in temperature, right? The faster those particles move, the energy associated with motion, the higher the temperature, right? And we're talking about the average thermal energy within the sample of matter that has those particles, okay? Heat, though, is a transfer of thermal energy. So basically, if something is hot, it's transferring that hot, kinetic energy that's basically the motion associated with energy. All of that is being transferred to something else, right? Like a hot cup of coffee, the water molecules, right? Coffee is mostly made of water. The water molecules in the hot cup of coffee are moving really fast, and that's why the coffee's hot, right? Because of the motion of the water molecules. But that thermal energy from the hot cup of coffee is being transferred to the surrounding air to cool the coffee down. Right? Now the water molecules in the cup of coffee are moving a lot slower because it's transferring its thermal energy to the surroundings, right? Which is just the air that's surrounding the cup of coffee. So heat is describing a transfer of thermal energy from, like, say, hot to cold, right? Like if I'm holding a hot cup of coffee, that thermal energy is being transferred to my hand, and my hand feels warmer, right, as a result. So temperature and heat are not the same thing. Really keep that in mind, because we're going to do practice problems related to heat and temperature, and there's no reason to get those two terms confused at this point. So when a system absorbs, let me go back to my laser pointer. When a system absorbs heat, its temperature changes by delta T, right? Let's say a system, the hot cup of coffee, in this case, it wouldn't be absorbing heat. It would be releasing heat to my hand that I'm holding the cup of coffee. The temperature is going to change, right? Let's say the hot cup of coffee started at 100 degrees Celsius, and it transferred its thermal energy to my hand. Well, now the hot cup of coffee is going to be, let's say, 70 degrees. So the change in temperature is 100 minus 70, right? So realize all of these concepts, they're pretty standard, but sometimes you just have to really go into detail of them to really get a good grasp of how they apply in the context of chemistry and chemistry problems, which we're going to look at in just a second. Okay. Let me go back to the pen. All right, the other thing we talked about last time was temperature changes and heat capacity. So when the temperature of something is changing, the question is how much of that is related to heat. And we know that heat is proportional to delta T. Okay, we saw this last time. Makes sense, right? If you have a large change in temperature, your energy term is going to be higher, right? But the other thing we need to talk about is the system's heat capacity. So the system's heat capacity is basically a measure of the system's ability to absorb thermal energy without undergoing a large change in temperature. So what does that mean? Well, that basically means if I'm trying to change the temperature of something, let's say the something is the system, right? We're talking about a system and it's trying to change temperature. The heat capacity is basically describing, well, how much energy does it take to change the temperature of that system by 1 degree Celsius, by 1 degree. So if you're trying to change the temperature of a system by 1 degree Celsius, how much thermal energy is required for that to happen? How much energy is needed in the form of heat to accomplish that? And we know that if heat is in terms of joules, right? Q is in terms of joules, and delta T is degrees Celsius, what does the heat capacity units have to be? It has to be joules over degrees Celsius. This makes sense because if you multiply joules over degrees Celsius by degrees Celsius, the degrees Celsius cancel, and you have joules on both sides of your equation here. So bottom line is you can quantify the amount of heat in a system by taking the product of the change in temperature times the heat capacity of that system. Okay? So we talked about that last time. And then we said, well, what if we want to define the system as something specific, not just the system? Because a system could be many things, right? A system could be, let's say, your pan on the stove with some water in the pan, right? If your pan is absorbing heat from the stove, right? Let's say I turn the stove on, the burner on, and the burner's on, and the pan is absorbing heat, but the water in the pan is also absorbing heat, right? So the system in that case would be the pan and the water, right? But what if you just want to talk about the heat capacity of something specific, right? Like, just the water, right? Or just the metal that the pan is made of. So every substance that exists has its own specific heat capacity. And basically all that means is the amount of heat that is required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay? We talked about this last time, how water has a really high heat capacity, 4.18, and this is a number that you guys are going to have to memorize. You don't have to memorize any of these other numbers on the table, but water is a really important one. Okay. Notice that this number is higher than a lot of the other numbers here. We talked about last time why that is, right? Why does water have such a high heat capacity? Meaning, why does it require that much heat, 4.18 joules of heat, to raise the temperature of water by 1 degree Celsius? And how much water? Remember, 1 gram. Right? This number is telling you how much heat is required to raise 1 gram of water by 1 degree Celsius. Pretty high number relative to everything else. And we said the reason for that is water tends to stick to each other pretty good, right? Like a couple of water molecules, you can imagine a lot of water molecules floating around, and they really want to be close together, and it's really hard to detach them from each other, right? It takes a lot of energy to detach them from one another, which is why it has such a high heat capacity. And we'll talk about the reasons why water likes to stick to each other pretty nicely relative to other substances. But that's the case for water right now. We don't need to know the reason why. We just know that water does, and all of these other elements, on this table have their own heat capacities, specific heat capacities, a lot lower numbers, but nonetheless, those would have to be given to you in a problem that requires you to use these specific heat capacity numbers. Now, where would you use these numbers? Well, if you want to quantify the amount of heat that a system has, well, we have to equal it to the mass of that system, right? So let's say that system is just water. So if I'm trying to figure out how much heat is required to raise the temperature of a sample of water, I need to know the mass of the water in grams, okay? I need to know the specific heat capacity of that water, and I need to know how much the temperature changed of that water. So let's say it went from 100 degrees Celsius to 70 degrees Celsius, right? So what's the change in temperature? It went from 100 to 70, so that's 30, right? So a certain amount of change in temperature, which is in degrees Celsius. The specific heat capacity, what should the units be for that? If we know the heat is in terms of joules, joules equals grams times the specific heat capacity times the degrees Celsius. Well, if we want grams and degrees Celsius to cancel, we need to put it on the bottom of the fraction, and we need joules on the top. This makes sense because the grams cancel and the degrees Celsius cancels. And now joules is equal to joules, right? The unit on the left has the same unit on the right side of the equation. So bottom line is you can use Q equals MC delta T to quantify this relationship between heat added to a given amount of substance and then the corresponding temperature increase, okay? We've done some problems related to Q equals MC delta T. Okay, so we did practice some problems. I'm not going to go over them again. You can go look at problem set 23. I'm just recapping all this because we're going to use all this information for the next concepts that we're about to introduce. Okay, so all right, so thermal energy transfer. We talked about how a system's energy could be measured in the form of Q equals MC delta T, right? But what if now I have the Q equals MC delta T of the system and I have the heat from the surroundings, right? So remember, there's not only a system, but the surroundings come with it, right? You can't just have a system and not talk about the surroundings. The system is impacted based on what's happening to the surroundings and vice versa. So if I have Q of the system, that's going to have its own MC delta T, right? M times C delta T. The surroundings is also going to have its own MC delta T. That makes sense, guys, because if some energy was packed in the system and it released it to the surroundings, if the Q of the system has an MC delta T, the surroundings also does, right? It makes sense that that's the case. And I think you guys did a lab on this where you took a piece of metal, you heated it up, and then you put it in some water, and you saw how the water's temperature changed, right? I think you guys did a lab on that. But bottom line is that if you have some sort of hot piece of metal, let's take a look at this figure here. You got a hot piece of metal, and it's transferring its thermal energy to the surrounding water. So the metal is the system in this case, and the water is the surroundings. And if I want to figure out, how much energy was transferred from one to the other, I can set these equal to each other, because whatever energy the system had, and it lost it to the surroundings, we can set them equal to each other. And there it is, right? Q metals is equal to negative of water. By the way, don't get confused about the negative sign. You're probably wondering, why is that negative? Well, if the system is going to lose energies to the surroundings, let's just think about this. Right now, we can say that, let's say the system, which is the piece of metal, is losing energy to the surroundings. If it's losing energy, we can have it be negative, and the system is gaining that energy. Now, I know this looks different than this, but realize it's the same thing. Because what if I multiplied this entire thing by a negative? Right? And I'm allowed to do that. If I'm going to multiply one side of an equation by negative, I can do the same thing to the other side. So I'm multiplying the entire equation by a negative term, and now I'm going to get negative times negative, which is positive. Q system, the heat of the system, is equal to negative, right? Because negative times a positive is a negative, Q surroundings. Okay? Which is basically this equation. Right? So all we're really doing, don't pay attention too much on the signs, right? Because all we're doing is we're trying to quantify the amount of heat that was exchanged. We're not trying to figure out, whether something lost energy to something or gained energy. We're just trying to quantify the amount of heat that was exchanged between one thing to another. And in this case, it's the metal and the water. Okay. Now, as I said, if everything has its own mc delta T, the metal has its own mc delta T, which is right here, right? The mass of the metal times the specific heat of that metal times the change in temperature is equal to the negative of the surroundings, which in this case, the surroundings is water. We need the mass of the water, specific heat of the water, and the change in temperature of the water. Now, let's practice a problem that is related to this concept of thermal energy transfer from one object to another, or let's just call it system to surroundings. So here we have the first one. It says a 32.5 gram cube of aluminum, initially at 45.8 degrees Celsius, is submerged into 105.3 grams of water at 15.4 degrees Celsius. What is the final temperature of both substances at thermal equilibrium? Assume that the aluminum and the water are thermally isolated from everything else. So basically what they're saying is that the, aluminum and water, no energy is being lost to any other surroundings, right? The thermal energy is just being transferred from the aluminum and the water, and there's really nothing else going on, just between aluminum and water. Okay, everything else is isolated from that situation. So, okay, what piece of information do we have here, and how do we solve this problem? So, we just said that Q of the system is equal to negative Q of the surroundings, right? And the system in this case is the aluminum metal. So I'm just going to say Q of the aluminum is equal to negative Q of water. Water is our surroundings. Okay. And now let's elaborate on the Q part and write it in terms of mc delta T. So Q of the aluminum is equal to the mass of the aluminum times the specific heat of the aluminum times the delta T of the aluminum. This is equal to the negative of the mass of the water times the specific heat of the water times delta T of the water. Now, one important thing to keep in mind here is that the final temperature once both of these substances exchange energy, the final temperature of both of them is going to be equal. Now, why does that make sense? Well, if something is hot and the other thing is cold, right? In this case, the metal is hot and the water is cold. The hot metal is making the water warmer, right? And the metal is becoming colder, right? At some point, both of those objects, or both of those systems, I guess that you can say, are gonna be the same temperature, right? The metal is losing some temperature to the water, and the water is gaining a certain amount of temperature. At some point, they equilibrate, right? So bottom line is that the final temperature for both the aluminum and the water is going to be the same. So what does that mean? That means I can rewrite this. I can say that the mass of aluminum times specific heat of the aluminum times the final temperature, T final, minus T initial of the aluminum. But the final temperature is going to be the same for both the water and the aluminum. So I'm just going to call that T final. I could do the same thing on the right side, where I could say the mass of water times the specific heat of the water times the final temperature minus the initial temperature of the water. Okay. And now I can start plugging stuff in, because what does the question want from you? They want the final temperature. Okay. And like I said, both substances are going to have the same final temperature, both the metal and the water. So what's the mass of the aluminum? Did they give us that? Yep, they said it was a 32.5 gram cube. Now, what's the specific heat of aluminum? That is something that you have to look up at a table, and the table would be given to you. If this is on an ACS exam, they would give you this. Okay, but check this out. Aluminum has a specific heat capacity of 0.903. So let's use 0.903. What's the units for specific heat? That's the amount of heat over gram times degrees Celsius. Right? The amount of energy it takes to change 1 gram of aluminum by 1 degree Celsius is 0.903. Okay. All right. Now, what's the final temperature? Well, we're trying to find what that is, so we're going to leave that alone. But we know the initial temperature of the aluminum. They gave that to us, right? What was the initial temperature of the aluminum? It was 45.8 degrees Celsius. And we don't have to convert that to Kelvin, because the units for specific heat capacity is in degrees Celsius, so there's no need to change anything. All right, this is equal to negative, what's the mass of the water? Did they give us the mass of the water? Yes, they did. 105.3. 5.3 grams of H2O times the specific heat of water, which we know is 4.18 joules per gram times degrees Celsius. That might not be given to you. You would have to know the specific heat of water. All right, and now we need the final temperature, which we said we're going to leave alone. And the initial temperature of the water, they told us, was 15.4 degrees Celsius. All right, so we have everything we need. The only thing we need to solve for is T final. And with a little bit of math, with a little bit of rearranging, which I'm sure you guys know how to do, okay, you can solve for T final. When you solve for T final, let me see if I have this math worked out. Yeah, I got, whoops. I got 17.3 degrees Celsius. Okay. Now, realize that there's many ways you can go about this. You can multiply some of these terms and move some stuff around, right? I find it easier to just move everything over on the left and just have T final left alone on the right. You guys realize that you can multiply these two terms right here, and whatever the answer is for this, some number, right? When you multiply those two, you can then distribute whatever that number over to both of those. You could do the same thing on this side, get a number for these two, distribute that over, right? And then, you can move some of the numbers over and solve for T final, and you should get 17.3 degrees Celsius. If for whatever reason you're having a hard time with the math on that one, you can come talk to me or your recitation instructor on how to get that. But at least you know the setup for this problem and how to solve for the final temperature once the aluminum and the water have reached thermal equilibrium. Okay, and just to ensure that you got this down, here's a practice problem that will be on a problem set. Okay. I think this is on problem set 23. If not, it'll be on the next one. But I will post answer keys for this as well. I would like for you to work through this problem and see if you can apply the concepts that we just learned in this video to this particular problem. Okay. So in this one, they're just asking for the mass of the copper block. What did they tell you? They said that you have a block of copper. You don't know the mass of it, but you know the initial temperature of the copper, and you know the initial temperature of the water that it's submerged in, and the mass of that water that it was submerged in. So you have the initial temperatures of the metal, copper metal, and the water. They told you what the final temperature of the two substances are once you've reached thermal equilibrium. So you have T final. And you're just finding the mass of the copper block. So if you do the same setup we did last time, right? All we're doing is we're solving for the mass of, in this case, it would be the copper, okay? You would need to get the specific heat of copper, but you can get that from this table, right? The copper specific heat capacity is 0.385, so you would need to use that number in that problem, okay? All right, we're going to talk about one more concept in this video before we wrap up to the next video. The last concept for this video is going to be related to work, and particularly pressure volume work, which I'm going to explain what that is. So why are we talking about work now? Well, we talked about heat, right? And remember how we said that energy could be transferred from a system to the surroundings in the form of either heat or work, right? And when energy is transferred in the form of heat, we know how to quantify that heat, right? How do we quantify that heat? Use Q equals mc delta T, right? Or if you have a specific, if you have the heat capacity of a system, you could just do Q equals the heat capacity of that system times the change in temperature. Bottom line is there are multiple ways of going about calculating and quantifying the amount of heat that's being transferred from one substance to another. Usually it's in the form of Q equals mc delta T, but you could also have Q equals C delta T, and C being the heat capacity of the system. But now we need to figure out how to quantify the amount of energy that's done in the form of work. So we're done with heat. We're going to look at work now. And we know that we can calculate the heat associated with a system based on some change in temperature, right? Delta T is in Q equals mc delta T. But now we can calculate work. Let me go back to my laser pointer here. We can calculate work associated with an observed volume change. So if we want to calculate heat, we look at a temperature change, right? Delta T. If we want to calculate work, we need to see some sort of volume change, aka, I'm going to go back to my pen. delta V, right? That's a change in volume. Change in temperature is delta T. But if I want to calculate work, I need to figure out how the volume changes. We're going to talk about why the volume matters so much. So a chemical reaction can do several different types of work. Okay, it could do several different types of work, but we're going to limit our discussion to just pressure volume work. What do we mean by pressure volume work? What we mean by that is when a force caused by a change in volume acts through a distance against an external pressure. So what exactly do we mean by this? Well, a classic example of pressure volume work is when you're looking at a cylinder, what's happening to a cylinder in your car, right? When your car is running, what's happening? Well, you have some sort of combustion reaction, and that combustion reaction is causing a change in volume in the cylinder, and it's doing work against some external pressure, that external pressure being the pressure that's surrounding the cylinder, right? So it's doing work on the surroundings, and it's pushing by increasing its volume some external pressure. Okay. Let's dive into that concept a little more. So remember how we defined work. Remember how we defined work as some force acting on a distance, right? Like you can imagine, I'm pushing a box across the floor or something like that, right? The force is, me applying a force on a box to move it across a certain distance, right? That's doing some work. But if we're talking about work in terms of a volume change, if let's say I have a certain, let me go back to my pen here. If let's say I have a certain let's say this is a piston. And right now, we have a certain volume here. And right now, I want to do some work. So what do I mean by that? Well, right now, that there's a certain volume. If I try to move this piston up, I'm moving it against some external pressure, right? There's some pressure going on in the surrounding cylinder, right? Let's call it air. Let's say there's some reaction going on here. Some chemical reaction is going on in here. Right? We can think of the automobile engine, the car engine. Imagine I have some sort of combustion reaction here, and it's moving this piston up against an external pressure. The pressure in the room, let's say, is just 1 atm. Now, to do that, we need to do some work to move it up, right? But that work is as a result of some force that's pushing the piston up times a certain distance that it's moving that piston, right? And remember that we define pressure as a force per unit area. We talked about this with gas laws, right? How if you have a certain amount of force per unit area, that describes a pressure. What do we mean by force? Well, gas particles, right? Imagine we have some amount of gas particles, right? Air is made of gas. Let's say we have the gas particles from the air bumping into the walls of its container or bumping into some area, right? If the molecules from the air are bumping the walls, the area that it's bumping into pretty hard, aka really large force on that area, the pressure is going to go up. If the gas particles are not hitting the walls of its container or the area with a good amount of force, then the pressure is going to be low. Right? So that's why we said that pressure is equal to force per unit area. Now, we can solve for the force if we rearrange the equation. And notice how we rearrange the equation over here. We multiply both sides by area, and we get force equals pressure times area. And you're going to see where I'm going to get with this. You could probably already tell. If the work is equal to some force times the distance, but we just define force in terms of pressure, why don't we take, pressure times area and plug it into the work equation? I'm going to do that on the next slide. Okay, there it is. So when the volume of a cylinder increases, it pushes against an external force, right? So that force is equal to pressure times area. Why is there an EXT here, right? We didn't have EXT before. We just said force is equal to pressure times area. We're going against an external pressure, right? We just said that if we're trying to move this piston up, here's a better graphical representation than the one I just drew. But if you're trying to move the piston up, you're pushing it against some external pressure. Where's the external pressure? Here's the external pressure. Right? The pressure of the room, basically. Now, we just said that work is force times distance, right? So we define the force as the external pressure times area. We plug that in, and now we get work is equal to the external pressure times A, area, times the distance D. Right? We're not doing anything crazy, guys. We just took the work equation, and we took the force in the work equation and replaced it with pressure times area, because we got that from over here. That's all we're doing. But now we can simplify this even more, because you guys know that area is length times width, right? And distance is some sort of height, right? If the piston travels some distance, if it's going from here to here, if the piston's going up, right, notice there's a change in height. And you guys know what length times width times height is. That's a volume. So, bottom line is, if you have a change in volume, right, which is basically what this is, because distance we're defining as some change in height, right, delta H. So the work is actually equal to the external pressure times area times the change in height. Okay? And area times change in height is change in volume. So now we can simplify this even more, right? Notice what I did here. Work is equal to the external pressure times area times change in height, which is the same thing as change in volume. Okay? So we have a new work equation. Have to constantly switch back and forth between the pen and the laser pointer. But there it is. Now, these are some really important notes on these bottom 2 points here. It says as the volume of the cylinder increases, right? Meaning going from here to here, the volume went up by this much, right? Work is done on the surroundings by the system. So W should be negative. We talked about this earlier from the table we saw in the first couple of minutes of this video, or I guess first 10 minutes or so. We saw that table that W should be negative, right? If the work is being done by the system on the surroundings, which is the case here, right? Isn't work being done on the surroundings by the system? So W should be negative. But if the volume is expanding, delta V should be positive. That makes sense, right? You had a larger volume at the end than you did in the beginning. So the change in volume should be positive, right? If the final volume is larger than the initial, final minus initial should be positive. But wait a minute, we don't have a negative term here. Where's the negative? There's no negative here. But we know W should be negative for positive expansion, right? So if you're expanding a cylinder, how can we get this term to be negative? So we need to add a negative term. For W to be negative and delta V to be positive for this expansion, we're going to put the negative sign right over here. Now you're probably wondering, well, how does that make sense? How can we just put a negative there? Well, if we know we're trying to have negative W P external times change in volume, all we're doing is we're moving the negative over. Right? Just multiply everything by a negative and transfer the negative. So now negative times negative is going to be positive, right? That's why there's a positive W here. But then negative times this whole thing right over here is just going to be negative. So that's why the negative belongs here. Okay, nothing too crazy, guys. We're just adding a negative term to describe a positive expansion for work. I'm just going to erase all of that. You guys get the idea. But this is the equation that describes work for pressure and volume associations. Okay. All right. Let's do a practice problem related to pressure volume work. So, question reads, to inflate a balloon, you must do pressure volume work on the surroundings. If you inflate a balloon from a volume of 0.100 liters to 1.85 liters against an external pressure of 1 atmosphere, how much work is done in joules? So whenever I see the term pressure volume work, I'm going to think to myself, okay, well, let's use our equation. W is equal to negative external pressure times the change in volume. And remember that change in volume is V final minus V initial. And they told you what that was. They told you that you started with a volume of 0.100 and you went to 1.85. So this is the final volume, and this is the initial volume. So W is equal to, and they also told you what the external pressure is, 1 atm. So let's just plug that in. It's going to be negative 1.00 atm times your final volume, which is 1.85, times your initial volume, which is 0.100. Okay, when you do this math, not times, I need a negative. Sorry, we're subtracting here, not multiplying. Okay, so now this is just going to be, what, 1.75 liters times 1 atmosphere. Remember, this is negative. This is going to be equal to 1 times 1.75, which is negative 1.75. Now notice what the units are. You're multiplying liters and ATM. So it's just liters times ATM is equal to the work. Now that's kind of weird because we never talk about work in terms of liter times atmosphere, right? Whenever you're trying to think of work being done on something or a system doing work on the surroundings, whatever the case may be, the unit should be in a unit of energy, right? If Q is in terms of joules, right? Q is heat, heat is in joules. Work should also be in joules, right? Because remember that the change in internal energy is equal to Q plus W. And if Q is in joules, work also has to be in joules. Right? Joules plus joules equals joules, right? It's just units here. And we know that the internal energy, delta E, is in joules. So everything has to be in joules, but this is not. This is in liters times atmosphere. And you're probably wondering, well, how the heck do we get from liter atmosphere to joules? Because that's what we want. There is a conversion for that. Okay? And this conversion would be given to you. It just wasn't given in this problem. But if I were to quiz you on this or give you an exam on this with a problem like this, I would give you that conversion. So I'll just tell you that 1 liter times atmosphere is equal to 101.3 joules. Okay? So that's the conversion. And you guys know how to do conversions, right? If I have negative 1.75 liter times atmosphere, I know that for every 1 liter times atmosphere, why am I putting that on the bottom? Because I want to cancel liter atmosphere. I'm going to put the 101.3 joules. Notice liter times atmosphere cancels. And we're left with whatever that is. It's going to be negative 177 joules. 3 significant figures, right? Because that's the lowest amount. There's your answer. So what is this basically telling us? This is telling us that negative 177 joules of work was lost by the system and performed on the surroundings. Right? If I drew an image of this, imagine I got my piston right over here. This is my piston. And remember, we started at a certain volume, 0.100 liters. And there's some external pressure here, P external. And they told you is 1 atmosphere. So we're trying to basically move this piston upwards. And if we're moving it upwards, we're increasing the volume from 0.100 liters to 1.85, right? We're increasing the volume if we move the piston up. But if we got to move the piston up, we need to do work on the surroundings because there's an external pressure we need to do work against. And how much work did we need to do against an external pressure to move the piston up from 0.100 liters to 1.85? If we wanted to expand the volume of this, we had to do this amount of work. 177 joules of energy needed to be provided to move the piston upward, right? And the system, this is the system. The external pressure is, in the surroundings. But the system had to do negative 177 joules of work to get this to happen. That's all this problem is really telling us. Right? Notice we're not trying to quantify the amount of energy in the form of heat. We're quantifying the amount of energy in terms of work. We already looked at heat, and this is just looking at work. Okay? All right. To make sure you nail this concept, here's a practice problem related to this. I think this is on problem set 23, but if it's not, it's going to be in a future problem set. Nonetheless, it will be provided on Moodle and the answer key to it. Give this a shot. This might show up on a quiz or an exam, this type of problem. So just make sure to be able to take the information given to you and figure out what they want. What do they want in this case? They told you a cylinder equipped with a piston, right? Same situation we had before. Expands against an external pressure of this time is 1.5 atm, not 1.00. They told you the initial volume, and they told you the final volume. Right? Initial, final. How much work is done? So you can go ahead and calculate that yourselves. Okay? All right. That pretty much concludes this video. So again, just to remind you, this is section 7.3 and 7.4 from your text. And this is associated with objective 12. So the next video is going to be on section 7.5. So stay tuned for that. Oh, before we go, there's another practice problem. Didn't even realize this. But there's another practice problem where, in this case, you're asked to calculate the work that's done, but they said, in addition, 875 joules of heat is emitted. And they're asking what is the delta E for the burning of the fuel. Okay? So guys, just remember before we exit this video that delta E is equal to Q plus W. You can solve for W because W is equal to negative P external times the change in volume, right? They told you the change in volume right over here. They told you the pressure. So you can calculate for work. And you guys know that for every 1 liter times ATM, there's 101.3 joules. So you're going to get your answer in liter ATM, convert it to joules. But then notice they gave you Q, heat, right? And when heat is emitted, what does that mean? If heat is emitted from the system to the surroundings, it lost heat to the surroundings. So if it lost heat from the system to the surroundings, it has to be negative. So this is going to be negative 875, right? Plus whatever joules you get from this is going to tell you what delta E is, okay? This is just to kind of guide you through that problem. All right, I don't think there's any more practice problems here. Let me see. Yep, that's the end of it. So thanks for listening and stay tuned for the next one, okay?